Um, can you guys hear me? Okay. Hi everyone. Today I'm going to talk about HDFS, what's new and what's coming in the future. Let me just talk about myself. I've been a long-term committer and a PMC member for Hadoop project. I am an architect at Hortonworks and I'm one of the co-founders at Hortonworks. I've been working on HDFS for almost more than 4.5 years. Mainly, Hadoop, and my main focus has been HDFS. Today, we'll talk about, in the agenda, we'll talk about what are the new features that are coming up in HDFS. We'll also talk about some of the major architectural changes that we are thinking of for HDFS that's going to come in the future. There we'll cover some of the short-term things that we are thinking of and long-term, maybe next year kind of features as well. We in the HDFS community, we have been hard at work. We have been looking at various features that are in demand in Hadoop. Some of these features are in the areas of scalability, performance, improving the performance, and enterprise features, and some of the operability improvements to make it easy to manage Hadoop clusters. We have also been making some enhancements where now that the Hadoop ecosystem is growing, we have been making changes for other projects in the ecosystem to work really well, such as HBase. We have also been trying to expand Hadoop use cases and platforms supported for Hadoop. Some of the use cases that if you see, we are going from batch processing to real time, things like that. So we want to expand the use cases where Hadoop is applicable in. And before this talk, I did some analysis on how the HDFS community or Hadoop community in general, how it's been contributing. So I counted in the trunk alone last year, since last March, I counted more than 2,000 contributions made by various people. It's almost 1 million lines of code that has changed in HDFS. I also counted 150 contributors, and that's a lot of, that's a diverse community. That goes to the theme of what Matt said about, more people jumping in, with their contributions. I also counted, around 80 new contributors in the last year alone who have done, less than 3 patches. So the community itself is growing. I also looked at HDFS and the common, which is a part that is closely tied with the HDFS, and I see roughly 350K lines of changes that are contributed by the community. So all this hard work, we have been doing it on a rock solid foundation. I want to do a quick overview of some of the things that we have done in the HDFS that worked really well for us, and some of the things that are coming as features, and some of those things are being changed, starting with some of the early design choices that we made that has made HDFS simple and robust. Let's look at some of those design choices. HDFS decided to use the local file system available on the operating system to store the data. This has helped us in building our storage on top of something that is really reliable, like ext3, ext4, instead of having to build our own storage on top of raw disks. The other choice that we also made was using replication, where you have multiple replicas of data for robustness of data, instead of going for RAID array, those other kinds of technologies. This has also helped us in terms of reliability. The one last thing that we also chose is to use one single name node as a master metadata server for the entire cluster. And I'll revisit this in some of the features that I'm going to cover in the future. Quickly looking at some of these decisions and how it has worked out, in a study that we did on Yahoo clusters, and Yahoo has more than 25 clusters, around 44,000 nodes running Hadoop. We did a study of reliability of data, and we looked at in around 2009, 2010. We saw that we had more than 7 nines of data reliability. And some of the issues that we found that caused some data issues have been fixed since 2009. We also looked at number of failures on the name node, and we found that it's roughly 0.38 failures across 25 clusters. Now you would, if you're going to ask me what is 0.38 failures, it's 13 failures across 25 clusters. Right? We also, because of the choices that HDFS has made, the operability is a lot simpler. For example, one of the design choice was, the nodes come and go, nodes have failures, disks have failures. This is particularly true for large clusters with a lot of nodes. And the design choice was, nodes fail, and the system needs to handle the node failure instead of having some operator to go and fix the issues. This has worked out really well. So in Yahoo and in some of the other large clusters that I've seen, we have one operator handling 3,000 nodes, the entire cluster, right? So all these are because of the design choices where we have assumed that nodes fail, disks fail. We also, because we made the choice of multiple replicas and distribution of replicas across many nodes, unlike RAID, where if there is a disk failure, you have to rebuild the RAID. In case of HDFS, multiple nodes together try to repair a loss of a disk or loss of a data node. And that happens in minutes versus many hours that takes in case of RAID arrays. Right? Finally, the other thing to note is because we have a large user base, we have HDFS proven in some of the very large deployments. There is a deployment at Facebook which has one single cluster with more than 100 petabytes of storage. We also have a cluster at Yahoo which has more than 4,500 nodes in a single cluster. We also have clusters where more than 400 million files are stored. So unlike some of the other systems where people say, we are using 64-bit for tracking files and hence we can store exabits, in case of HDFS, we have real deployments that show how HDFS scales, and we have supported large storages. Also, HDFS is deployed on many, many nodes. Conservatively, I counted roughly 70K nodes that I know of where HDFS runs, right? So the advantage here is there is an opportunity for HDFS to get widely deployed and stabilize really quickly. Now, going over some of the features that's available in new HDFS, I covered the first choice that we made in HDFS, that is to use a single name node for the entire cluster. Now, the problem with that was single name node became bottleneck for scaling the namespace. So one of the features that we worked on in 2.0 is federation feature. The main goal of federation feature was just like Yarn, what Yarn did to MapReduce. The main goal of federation was to look at the abstraction of HDFS itself and try to abstract out the storage layer from the namespace layer. By doing this, what we essentially have is a generic block storage layer, and this block storage layer can be used by not only just the HDFS name node. You can also have other applications that could use the generic block storage layer. So this separation of abstraction is something that we have started out in federation. The other thing we also do in federation is add support for multiple name nodes and namespaces within a cluster. Now, this is for large clusters which require namespace to be scaled. This is a way where you can add more name nodes and expand your namespaces horizontally. You can scale them. This also gives an opportunity even for small clusters where if you want to isolate different applications to different name nodes and namespaces, that way, for example, you may have a namespace for HBase which doesn't interfere with, let's say, a name node that is being used by MapReduce. You could use these kind of isolations by using multiple name nodes. Is there a clicking noise? I mean, I'm hearing some clicking noise, so I don't know if somebody needs to fix. Hopefully it's better now. We also in federation, because you have multiple namespaces, we have added a feature called client-side mount tables, and that's a configuration-based mount table definition, which can be used for integrating all the namespaces together to get an unified view of all the namespaces within the cluster. The other feature that we also have been, and this is ready right now, is, like I said, we had single name node, and that was a single point of failure in HDFS cluster. One of the work that we have done, both in release 1.0 and release 2.0, was to add support for high availability for the name node. Essentially, what we have done is added a support for standby name node and support for failover. In release 1.1, we have a cold standby name node. Cold meaning, it doesn't have all the state of the active name node. It has to come up and load the state. And this is built using a shared storage using NFS. We have added support for failover using standard HA frameworks, such as Linux HA or VMware vSphere, which does the health check of the name node, and when the name node fails, it does a failover and brings up a standby. This HA framework is suitable. I mean, this HA solution is suitable for small clusters, around up to around 500 node clusters. Beyond that, because it's a cold standby, the failover times are much longer. We also, as a part of this work, we did look at all the other stack elements that are dependent on the name node. And here is an example of how the stack gets affected when name node, which is a core storage layer, is not available, and how we handle it using the full stack HA solution that we have provided. Now, here is an example of, a name node is running, it's running on a server, and this name node is being used by some applications, MapReduce framework, where you have job trackers and tasks running using this name node. And when these applications are running, if a name node fails, what essentially happens is the file system is unavailable for all the applications and MapReduce framework. And at this point in time, what we do is we have built, using full stack HA, we have built pausing of applications, and in case of MapReduce, the framework itself goes into safe mode where it pauses and doesn't allow all the jobs that are running to fail. So the cluster gracefully handles the unavailability of name node. And then the name node fails over. When the name node fails over to the other server, essentially all the applications and MapReduce jobs now resume with the new active name node that becomes available. So this full stack HA is not just done for MapReduce, it's also done for HCatalog. It is done for HBase, so that all the stack other projects that are dependent on HDFS gracefully handle some of these kind of failures and the failover that happens. Right. We also have been doing further work on high availability, and it's going to be available in release 2.0. Essentially, in release 2.0, we decided that if you look at release 1.0 HA solution, we use HA frameworks for such as Linux HA for doing the failover. Now we have a framework that is built into HDFS called failover controller. And essentially, what failover controller does is it provides the functionality that is provided by Linux HA. It essentially uses Zookeeper for electing an active name node in the cluster between active and standby. It also uses, through Zookeeper, it detects the failure of a name node, and either when a name node fails or when a name node health check fails, it performs a failover. I'll go into the details. I have an architecture slide, and I'll go into more details of how this works. We also removed the shared storage dependency that is there in release 1.0, which uses NFS for storing the metadata of the name node, and that becomes the conduit for failover. That we have removed now using Quorum Journal Manager that has been introduced into release 2.0. So let me go over the architecture of the HA solution that's available in release 2.0. We have an active name node and a standby name node. The name node has two kinds of states. One is block location. The other one is file system metadata. The block locations are kept hot in a standby by data nodes registering with both the name nodes. So data nodes register with both the name nodes, send the block reports. They also send all the block-related information, such as when a new block is received by a data node, it reports it to both the name nodes. That's how both the name nodes have the block-related state. As far as the file system namespace information is concerned, when an active name node accepts a change into the file system namespace, it writes it to edit logs. Edit log through journal nodes is also sent over to the standby name node, which is then read by the standby name node. Essentially, through the edit logs, the active is sending all the edits that are happening to file system namespace to the standby, right? So that is how standby now has hard state of what is there at the active, both block locations and file system namespace. Now, we also have two new modules called failover controllers. There is one failover controller running for each of the name node. And what failover controller does is it works with Zookeeper using ephemeral Z nodes. And when a failover controller can create an ephemeral Z node, that means that it is the leader, and it chooses one of the name nodes as the active name node. The other thing that failover controller also does is it periodically performs health check of the name node. So it keeps sending different kinds of requests to the active name node. And when the active name node either has a failure or doesn't respond back, it declares the active name node as dead and then performs a failover to the standby name node. So it is in charge of performing failover. The other thing that is also a key to note here is if a box that is running failover controller and a name node dies, the failover controller that is running on another box on the standby through Zookeeper detects that either the failover controller has died or the active name node has died or the hardware is not, hardware is dead, and performs a failover and takes over as active. Right? So that's the architecture of high availability in release 2.0. The other key feature that we are working on, which is really exciting to see, reaching its completion, is snapshots. Snapshots is to go over some of the use cases. A lot of file systems have ability to take snapshots. That is point-in-time state of what file system has. This is used in many ways. One of the ways is if an operator error or user error results in deletion of some data, you can go back to your snapshotted state, right? So that is to recover. In some cases, snapshots are also used for doing, consistent copy of file system from one cluster to another cluster. Right? So these are two frequently used users of snapshots. The snapshot feature that we are working currently on is read-only snapshot. The design allows read-write snapshot. Read-only snapshot meaning once you take a snapshot, you cannot write data to it. Or you have to delete the entire snapshot. You cannot delete a single file, right? So it's a read-only snapshot. And when we were looking at this feature, we had two choices. We could have done snapshots as a distributed mechanism. That is, name nodes work with all the data nodes that are in the cluster and create a snapshot. We took the second choice, which is snapshots are done at the name node alone, right? That removes the distributed mechanism, that the requirement for distributed transactions and the complexity that comes with it. So the snapshots, when you create a snapshot, it's a name node only operation, and the snapshot related data is kept only within the name node. We also looked at different use cases for snapshots. One of the use cases for Hadoop is a multi-user shared system, which means that you cannot have users going to administrator and asking for snapshots to be taken periodically. And in some cases, an application might want to make some changes, and if you're not sure, you may want to create a snapshot before running your application. So from that regard, we wanted to allow snapshots both at the user level and at the admin level, which meant that user should be able to snapshot his own data, resulting in this decision that you can have snapshot taken for the entire file system namespace, or you can take snapshots at a certain directory level. This requires doing multi-level snapshots and also snapshots which are nested, right? So we support both of them in the feature that is upcoming. The other key thing is when we added snapshot feature, we wanted snapshot creation to be really efficient, right? So today, because we now do everything in the NameNode, the snapshot creation is actually instantaneous. We also wanted to keep, given that NameNode stores everything in memory, we also wanted to keep snapshot-related data really to the minimum so that it doesn't affect NameNode memory consumption. So we have done some optimizations on how much memory is used for snapshots, and I'll go into those details on how we do this. We also wanted to make sure that regular file accesses that are non-snapshot accesses are not affected by how we store the snapshot. So the way we store the snapshots does not affect the latency of operations for your regular non-snapshot access as you do today. Right. Going into design details, details of snapshots, we use a data structure called persistent data structures. This is a data structure used for tracking changes to directory trees or lists and things like that. And that is what we use in the snapshot. Every directory that is tracking snapshot, that is a part of snapshot, keeps the persistent data structure using diff list. So essentially, a diff list is nothing but if you've taken a snapshot, in that directory, let's say if you create a file or if you modify a file or if you delete a file, the diff list gets an entry to track the changes that have happened since the snapshot, right? So, and what we do is we don't have a materialized view of what a snapshot has. Snapshot's state is always obtained by adding the diff list state for that particular snapshot onto the current, right? So that way we don't take extra memory for storing the snapshot state itself. Because of these choices and diff lists are highly optimized, we can support a large number of snapshots in HDFS, right? Given HDFS is mostly, the use case is, you write once and read many, many times. And the changes that happen in HDFS is a lot less compared to number of files created and deleted. We can support millions of snapshots, and the number of snapshots that we can support is proportional to the changes accumulated since the snapshot is taken. I'll also go over some of the APIs and CLIs related to snapshot, just so that you get an idea of how some of the APIs change. We chose to use a lot of file system APIs are built around path, right? A string that gives you slash user, /Suresh, those kind of regular file system paths. We decided to keep snapshot access also based on paths. The advantage of that is the CLIs, the file system APIs that you use will continue to work even on the snapshot files and snapshot directories. So one of the examples of snapshot path is, you have a path, and then when you say .snapshot, HDFS recognizes it as a path related to a snapshot, and then you can give a snapshot name to identify a specific snapshot, and then you can give, let's say, a file or a directory name. And that's how we identify that file.txt comes from a particular snapshot. And given that we support these kind of paths, you can use file system APIs, you can use Hadoop CLIs, such as cat, copy, and they'll continue to work on the snapshots as well. We also, as I said, we wanted users to be able to take the snapshots, which means that an administrator takes a directory and then allows snapshots so that users now can go and start taking snapshots on their own. So DFS admin command has been added to allow snapshots on directory and disallow snapshots snapshot capabilities. We also have an FS command for creating a snapshot, deleting a snapshot, and of course renaming a snapshot, because snapshot name could be a way application codifies when the snapshot is created and how to use it, right? So we allow rename of snapshots also. We also have some tools where now you can see difference between a snapshot and a current directory, or a snapshot and a snapshot. The idea being you can see how much changes have happened since you have taken a snapshot. Also, you can also look at how many files are there only in the snapshot and they are no longer required in the system, right, outside the snapshot. This is an example where you have created a file and you took a snapshot, now you deleted the file, but the file continues to live in the snapshot. So you could go look at how much data is consumed by snapshots alone, and then you can choose to either delete the snapshot or understand how much memory, how much disk space or number of files is consumed by the snapshots. Current status of the snapshot work is it's almost complete. Testing is in progress. All this work has happened in a separate feature branch, and we are getting ready to merge it into trunk. Given that now we have Ambari for managing Hadoop, and if you guys have not, if you guys don't know about Ambari, there is a talk tomorrow about Ambari. You should attend it. It is a new Apache project for managing, monitoring, and installing Hadoop clusters. And so we are making some changes into Ambari to make snapshot management very easy. You can browse the snapshots, you can look at the number of snapshots. So all those capabilities will become available in Ambari. What other things are we working on in HDFS? One of the things that we have been optimizing for a long time is the performance improvements in the I/O of I/O subsystem of HDFS. We made a change to use new SSE 4.2 Intel instructions for doing CRC calculation. With this optimization, where you use the new instruction sets for doing CRC 32 calculation, we are seeing approximately 3 times the CPU. CPU is reduced by almost a factor of 3 on the read paths. All the CPU that is saved in the read paths will help in giving that CPU to other tasks that are running within the cluster. We also made some read path improvements where we manage the buffer copies better, and we have reduced the number of copies that's being made in the read path. That's made some of our reading side much more efficient. We added sometime last year short circuit capability, and this was done for HBase. The idea being HBase does a lot of random I/O, and doing random I/O over a data node protocol over socket was not very efficient. So we added a change for HBase where we directly allowed HBase to read the block file instead of having to go through the data node. That resulted in 2 to 3 times faster random reads, and this also improved HBase kind of workloads by reducing CPU and by making reads faster. We also have a variant of this. This is going to be the replacement for short circuit. Short circuit configuration was more complex, and the security model was not very good. Now we have Unix domain socket-based short circuit replacement where you can use Unix domain sockets to get at the file, and you don't have to go through the data transfer protocol over a socket anymore. This has shown really good performance as well. We also made some I/O improvements in terms of how well file system can manage buffer cache by using fadvice, and this has also resulted in much better buffer cache utilization and improvement in the I/O in HDFS. So all these improvements that we have been working on has made the I/O on HDFS anywhere from 2.5 to 5 times faster. Some of these changes are, all these changes are in trunk, and we have been also backporting some of the changes into release 1 so that people who are using release 1 can benefit out of these kind of performance improvements as well. There is other, HDFS community has been, working on a lot of other features. I will briefly go over some of these features. In release 2.0, you have a new append pipeline that is much more robust, has lot stricter guarantees compared to the previous append feature. We moved our RPC implementation in Hadoop to protocol buffers-based serialization. This will help in in maintaining. This will make making backward compatible changes easier, and we plan to keep much stricter backward compatibility from 2.0 onwards. It won't be just API compatibility; it will also be wire protocol compatible. We also have made some changes where some of the restrictions that we had in the past in terms of software version checks have been relaxed. This has paved the way for rolling upgrades in dot releases. We have also made some changes for other projects in the Hadoop ecosystem. One of the examples is we added a new state for the data node. So today data nodes are either live or dead. And before a data node can be declared dead, it takes 10 minutes. We have added a new state called stale state. Now stale state is something where if a data node does not heartbeat with the name node, for a period of, let's say, 30 seconds. It's configurable. For a period of 30 seconds, then since you don't know what the data node state is, we don't want to declare it as dead, because declaring it as dead means we need to do replication for all the data that is there in the data node. We don't want to create those unnecessary replication work. However, for applications that are latency sensitive, the stale, if we declare some data nodes that have not done heartbeat for, let's say, 30 seconds as stale, those applications now can choose another data node to read the data from, and they don't have to retry and wait for a minute before switching over to another data node. So this kind of state is useful not just for HBase, it's also useful for other applications that are coming up in the ecosystem which are latency sensitive. We also have made some enhancements to block placement policy. In Hadoop, the default block placement policy that HDFS comes with is pluggable, right? So you can have your own implementation. Now we have two new implementations of block placement. One for which is aware of virtual machines, so that you place the blocks across physical machines instead of just across data nodes. We also have, and this is due to come out, a block placement policy suitable for cloud kind of infrastructure where it considers failure domains and upgrade domains, things like that. We also have now new features for encrypting the data, both RPC and the data that is being returned to data nodes. We currently are working on an NFS gateway. This is not out there yet. At Hortonworks, we are working on an early prototype, which is now beyond the prototype quality, to support NFS gateway. So that way you can mount HDFS anywhere and start using it just like your NFS file systems. We have also been hard at work trying to expand the Hadoop usage to other kinds of usages. In some cases for real time, in some cases to other platforms. One of the work that recently got into trunk was native support for Microsoft Windows, and so now Hadoop can run on other 40% or 50% of Hadoop server market where Windows is the choice of operating system on the server. So with that, I want to just recap some of the Hadoop has come a long way. It has come from web companies which were the main users of Hadoop to now enterprises. And I just wanted to quickly go over some of the enterprise readiness state of Hadoop and HDFS in specific. As you know, and as I talked about, storage fault tolerance has been the strength of HDFS for a long time. Given some of the studies have shown that we have over 7 nines of data reliability. Also, now we have added, because NameNode was a single point of failure, now we have added high availability support both in release 1.0 and release 2.0. We have support for standard interfaces. We have REST APIs. We have C APIs. Of course, there are HDFS Java APIs as well. We are now adding NFS, which will expand the number of standard interfaces we have. We made changes where wire protocols are now protocol buffer based and can support wire compatibility better across releases. And then we have now support for rolling upgrades, snapshots, and then disaster recoveries using DisCP. And then we have plans of improving DisCP further by adding such capabilities into Ambar itself. I'm running out of time. I'll quickly go over some of the work that we are planning to do in the future, and some of these features are something that will come in next 6 months, and some of the features are out there probably will happen next year. So some of the things that we are thinking of is in Federation, we started changing the abstraction of HDFS. What used to be a file system became a storage layer and namespace. We want to continue along these lines and add a few more fundamental abstractions into HDFS storage. One thing that we have started, it's already there in trunk. One thing we've been doing is today in HDFS, data nodes appear to the name node as one blob of storage, right? Just one storage. Now we want to make that more granular where name node can have awareness of data node as not a single storage, but collection of storages. Now what that brings is as servers become available with SSDs and other kinds of storages, that becomes visible, and now applications can start asking for not just, I want to write data. It could say, I want to write data in this class of storage, right? It could use SSDs or it could use this. We want to start working on some of those things. We also want to add newer level of details where you could start using not just node location, which is what Hadoop has, to disk locations. And this will start becoming more important in the frameworks that are coming up, like TES, where you don't want to schedule your work, which is latency sensitive, on a same disk. Instead, you want to do it on multiple disks, right? So we will start adding those kind of more granular addressing of storage within HDFS. The other thing we are also exploring is today all applications are forced to use file system interface, right? But not all applications really require file system interface. So we are considering looking at having block level APIs where you really don't care about renames and append to the file, but all you need is a blob of data, and then you want these blocks to be in a collection where you can insert data, remove data. You can do a lot more flexible things. And so we are exploring providing those as block level APIs. We also are considering adding more granular block placements. Today, the entire HDFS system has one block placement policy, right? So we are looking at supporting multiple block placement policies, and then you could choose perhaps at a directory level, this is what the block placement policy I need. And some of this will be useful for even other projects that are in the ecosystem like HBase, right? So the other long term, and this is something that will start towards the end of the year, is we want to explore adding maybe a key value store kind of an API support in HDFS. If not API directly on HDFS, at least enablers for those kind of APIs. There's a lot of interest in other communities and other projects to build key value store on top of HDFS. We also plan to start exploring making data nodes more structure aware. Today, data nodes are just blob stores where a client has to read the entire blob, and then the client applies the structure associated with the blob. Instead, we could have data node being aware of the structure, because of which, there are a couple of things that you could do. One is structure-aware data node could give only subset of data instead of client having to read all the data and reduce data movement. It could also do some kind of selection of data, aggregation of data for instead of doing it in the client, it happens at the serving layer, right? So those are other things that we are thinking of. Going further, this is as HDFS gets used in larger and larger clusters, we are considering doing some scalability improvements. One improvement that is applicable to even for not so large clusters is storing only partial state in the name node. So today name node has entire metadata in memory, but not all the files are hot files, right? There are cold files that are not accessed. We are exploring ways of only keeping partial namespace in memory. That way name node can scale to much higher number of files and directories. We also are thinking of adding an abstraction where name node will become a container of namespace volumes. That way you can support multi-tenant use cases, much larger namespaces better. We are also looking at supporting different kinds of namespaces. So today, the only namespace that is available is a file system namespace. So we could have maybe key value namespace, maybe just block container kind of a namespace. All this is possible because of some of the federation work that we did. We are also considering features to scale block storage further. This means we will have, we'll explore moving block management to data nodes. We will also add an abstraction where block, we'll have block collection or mega block groups is what, we call it as, and these kind of abstractions will come where the number of blocks supported in the data nodes itself can scale. Right. Finally, some of the recent high availability work that we have done is not, complete. We have, further enhancements in mind. One is in release 2.0, we want to look at all the other frameworks that are coming in, such as TASE, and extend full stack HA ideas into those so that they gracefully handle some of the HDFS related failovers. We are also looking at adding not just single standby support, multiple standby support. Current design does not preclude it, but we'll test them and make them easy to manage. The other thing that we are also thinking of is adding support for NameNode standby, where you can read the data and grow the number of operations HDFS supports. And then we further want to simplify the management by moving the metadata storage to HDFS itself. So that's what I had in mind. And here is a list of some of the myths and misinformation about HDFS. And I don't have time to go over it, but these are some of the things where people are misinformed or do not understand. So I just wanted to put it out there. Sorry, I've gone over my time. If you have any questions, I can take a couple of quick questions, and then other questions I can answer in a hallway conversation. So is there any plan to support cluster-to-cluster replication? So today, what we have is DisCP, right? So in a month or so, we will start enhancing DisCP to include snapshot awareness. We are looking at various ways. There are different use cases, and I would like to talk to you about what your use case is. One is you take data available in cluster and make it available in another cluster. The other school of thought is do a lazy replication as you're writing to another cluster. We are leaning towards the first one, and because the first one is a lot simpler to do, and it is, you can manage the schedules. You can also look at how much data is there in this cluster, and then, when to copy it. Those policies can be enforced. Doing replication in the pipeline, where one of the replicas is on another cluster, is a lot harder challenge, and this is something that, we may take up at a later point in time. What is the current status of? Replication storm. Okay, so today what you have is, if when data nodes fail, we have to replicate a lot of data, and that's the reason why we have 10 minutes time. However, I think there are some features that are needed where we may need to relax that even further, where if the entire rack becomes unavailable, we want replication to happen slower, right? So I think I've run out of time. Yeah. So I'll take the questions afterwards outside. Thank you.